The objective of any map is simple: communicating the spatial relationship of here to there. But achieving that requires overcoming a massive biological limit. The human eye is incapable of perceiving planetary scale. For most of our history, our natural perspective was restricted to what we could physically observe, from the peak of a mountain or the crow's nest of a sailing vessel. Overcoming that limitation meant realizing that accurate mapping cannot rely solely on drawing what is physically in front of us. It requires integrating geometric calculations, precise celestial observations, and eventually remote sensing technologies. While humans have always navigated via landmarks, the ability to organize the entire world into a single cohesive picture required moving beyond intuition. Mathematical cartography provided the shared framework necessary to translate local knowledge into a global system of mastery. Identifying and measuring the exact geometry of the sphere itself was the first major milestone in scientific cartography. This feat was first achieved in the 3rd century BC by the Greek astronomer Eratosthenes, working as a scholar at the Alexandrian Library in Egypt. This diagram shows the precision of his work compared to modern measurements. By tracking shadows, Eratosthenes arrived at an estimated circumference of 25,200 miles. When we place that next to the actual known longitudinal circumference of 24,860 miles, his ancient math proves remarkably accurate. Yet calculating the total size of the sphere was only a partial solution. Navigators needed a reliable system to organize and divide this massive, continuous surface. Building on the ideas of his predecessors, the astronomer and geographer Ptolemy devised a solution for spatial organization in the 2nd century AD. On this ancient projection based on Ptolemy's work, clear grid lines curve across land masses, a strict geometry of latitude and longitude. Today, parallels of latitude are spaced at intervals of 10 to 20 degrees, and meridians at 15-degree increments, structuring our modern global time zones. By locking the physical planet into this grid, Ptolemy transformed the Earth from a continuous wilderness into a precise, searchable database of coordinates. For centuries, map production was tightly controlled by monks whose illustrations prioritized theology over geography. That changed when the 15th century printing press placed charts directly into the hands of the public. Simultaneously, an age of ocean-going discovery launched an influx of geographic data from traveling merchants, generating a need for mathematically functional navigation charts. But this demand collided with an inherent physical paradox. To portray a round, 3-dimensional world on a flat, 2-dimensional sheet of paper, the geometry must physically tear or artificially stretch. The foremost mapmaker of the 16th century, Gerhardus Mercator, approached this geometric problem by engineering a specific mathematical compromise for maritime navigators. Mercator developed a distortion formula that arranged meridians and parallels so that sailors could draw a straight line between any 2 points. A ship could now steer a constant compass course along that vector without needing to adjust for the Earth's curvature. The trade-off for this navigational utility is severe spatial distortion near the poles, famously known as the Greenland problem. The math stretches the northern latitudes so intensely that Greenland appears to have the same landmass as all of South America. Perfect geographic reality was sacrificed for functional maritime survival. Maps are not intended to be flawless visual photographs. They are engineered tools designed to solve specific physical problems. While maritime navigation improved rapidly, creating mathematically accurate maps of inland, terrestrial terrain remained difficult well into the 17th century. The solution was spearheaded by Jean-Dominique Cassini, launching a multi-generational family project to scientifically map the entire landmass of France. Cassini invented a method for establishing exact positions on the ground by looking up. He calculated terrestrial longitude by carefully observing the orbital movements of Jupiter's moons. By triangulating local time and position against predictable celestial bodies millions of miles away, surveyors could systematically bypass local visual obstacles like forests or mountains. This visual record is the culmination of that technique, published by Cassini's great-grandson in 1793. The map catalogs roads, rivers, canals, and towns using strict geometric measurement rather than rough estimates. With the publication of these borders, France became the first country completely mapped by empirical scientific methods. By directing their lenses at Jupiter, cartographers achieved pinpoint precision on Earth, permanently decoupling mapmaking from human visual guesswork. In the modern era, the primary perspective of mapmaking has shifted far beyond the horizon. The most expansive tools of contemporary cartography no longer look out from mountaintops, but down from new orbital heights. Technologies like microwave radar bounce radio signals off a given surface, measuring precise return times to mathematically calculate vast physical contours and textures. Because it relies on returning wave frequencies rather than light, radar can penetrate dense visual obstructions like thick jungle foliage. Looking at this topographical map of the planet Venus, we can see the extreme applications of remote sensing. Radar cuts through the planet's thick atmosphere, proving that cartography is no longer limited by what the eye can see. Back on Earth, pairing this radar data with underwater sonar has allowed scientists to chart the hidden topography of the ocean floor. To access this data, modern surveyors and hikers carry handheld receivers linking directly to a navigation satellite system operated by the U.S. Defense Department. The process of measurement has inverted. We no longer calculate the scale solely by walking its surface, but by pulling invisible coordinate data down from the stars. The history of cartography is the continuous, rigorous refinement of spatial data processing. Whether a scholar is measuring shadows across the Egyptian desert, or a computer is processing orbital microwave radar, the underlying mathematical framework relies on the exact same coordinate grids. Cartography is pushing onto cosmic frontiers, but its singular, unyielding objective remains unchanged: communicating a precise sense of here in relation to there, no matter the distance. This video is brought to you by the IELTS FOCUS 08477059973, an English center specializing in IELTS preparation. We can only navigate spaces that we can reliably measure. Ultimately, our understanding of physical reality is only ever as strong as the mathematical grid we project onto it.